This is Intermediate Math Challenge 2021. Just a quick explanation of the rules before we get to it, because it's slightly different to junior and to senior. You don't lose any points for getting the first 15 wrong, so you may as well just guess them if you're unsure, or leave the guessing until last, just in case you have some kind of flash of inspiration towards the end of the paper. But you do lose marks for 16 to 25, so I would only guess 16 to 25 if you've narrowed down the options a bit. If you've got it down to a 1 in 2 guess or a 1 in 3 guess, then probably do guess it then, because statistically you'll get marks for it if you do. But yeah, those are the rules, and of course you want to get as many correct as you can. Let's go straight into it. So question one, number one, I'm probably not going to spend a lot of time on these kind of questions, because I mean this is literally just adding. There's nothing intelligent to do here. There probably might be some intelligent thing you could do, but it's not worth it. Just do that. Question number two, I mean you can just set this out if you are struggling to hold all of the information in your head. We'll say that today is Thursday. That's this piece of information here, which means the day before yesterday. So yesterday, day before that. So let's just count backwards. So that's the day that they're actually talking about, was 2 days after the day before my birthday. Now 2 days after this, or this is 2 days after Sunday, obviously. So sorry, it's 2 days after Saturday. And then if Saturday is the day before my birthday, that means my birthday was on Sunday. I'm not sure whether I explained that very well, but for me this is just a weird question that I think if you just sit here and think about it long enough, you'll probably get. Question three, again, just bid maths, I guess. Just do the brackets. Make sure you know what negatives are talking about. Two negatives make next to each other like this, just like a positive. Brackets do again first, and then this just ends up being 4 because those cancel. Good. Question four. So there are probably lots of ways to do this. The first thing we can immediately see is that we've got squares here. So that's 90 degrees, so is that, so is this, and so is that. And what I did was, well, the angle here, I just sort of saw that as being inside of this polygon here. And this polygon has 1, 2, 3, 4, 5, 6, 7 sides. So the total number of degrees in this polygon is 7 minus 2 times 180, because that's how many triangles fit into it. And now I've got that this angle is 90, as I've said, and so is this angle. And if this is 90 and this is 90, then that means that on the outside we've got 270 and 270. So now all I need to do is 900 minus all of these things, and I should get that thing there. And in the end it equals 44, I think, in the end. Good. Question number five. So these people have 90 sweets between them. May has 3/4 the sweets that June has. So what I said here was that I just said, as a ratio, I just said that June has 1. And then if May has 3/4 that June has, May has 3/4. And I know usually we don't write ratio in fractions, but it's fine. April has 2/3 the number of sweets that May has, so I just need to find 2/3 of that. Now this is nice because the 3's just immediately cancel. You get 2/4, which is a half, and so our ratio is a half to 3 to 4 to 1. Now fractions aren't as nice to work with as whole numbers, so if we just times everything by 4, we'll get 2 to 3 to 4. And just check this works. So May has 3/4. Oh yeah, 3 is 3/4 of 4, and April has 2/3. 2 is 2/3 of 3, so that's good. And now we just add. It's just a normal ratio question. 2 plus 3 plus 4 is 9. Divide 90 by 9 to get 10, times it up by 4 to say that June has 40 in total. Question number 6. So begin to list in ascending order the positive integers that are not factors of 240. Let's just list the positive integers quite far, and let's start ticking off numbers that are factors of 240. So 1 is a factor of 240 because 1 is a factor of any positive integer. And 2 is also because this is clearly even. This is also divisible by 3 because I know 24 is, so 240 must be. It's also by 4 because again I know 24 is, so 240 must be. It ends in a 0, so 5 must be. But at this point it's getting a bit more and more annoying to check where the numbers are. And whenever you're thinking about factors or even anything to do with number theory and integers, you always want to think about primes, prime factorizations in particular. If that's quickly prime factorization 240, well it's 2 times this, which is 2 times this. And that's 2 and 5, that's 2, 2 and 3, and so this is my prime factorization. I couldn't be bothered to write it out in order or in index form, but this is going to tell me a lot, because the fact that it's got a 5 in tells me that it's divisible by 5. Now I already knew that because it ends in a 0, but that's fine. The fact that it's got a 2 and a 3 in it means those two could just multiply to make 6, and so it must have a factor of 6. 7 is nowhere in here, and of course because 7 is prime I can't make it out in any other ones, so 7 is the first number on the list that's not a factor of 240. 8 is because there's 2 times 2 times 2 here, which makes 8. 9 isn't, because to make 9 I'd have to do 3 times 3, but I've only got 1 3. So 9 isn't, but 10 is because there's a 2 times 5. 11 isn't, again, same as 7, it's prime. 12 is a factor because 2 times 2 times 3, we also just saw it there, it's 12 times 20 is 240. 13 isn't, 14 isn't because there's no 7 to use, so I'd have to use 2 and 14 to get 2 and 7 to get to 14. 15 is a factor because I can use 2 and 3. 16 is because I can use 2, 2, 2, 2, which makes 16. And so 1, 2, 3, 4, 5, 6. And wouldn't you know, the last number on my list of arbitrary integers was the correct answer. It's almost like I planned this in advance. Okay, question number 7. So yeah, let's just put these fractions together. So this is 4 over 1, this is 2 over 1. If this isn't how you do fractions, it should be. As soon as you see an integer, just put it over 1. Make the denominators the same now, so that's 16 over 4, that's 4 over 2. Now we can take away. And now we can just do KFC. Right, so this times the reverse of this. There could be some cancelling we could do straight away, but I couldn't be bothered. It's just 30 over 12, cancel now for 15 over 6, which is 2 and a half, I believe, if we change that to mixed number form. Number 8, so 10 by 14 rectangles. So it looks like this is the shorter side probably, and this one likewise. So I think this is probably 14 and this is 10, and this is 14 and this is 10 here. Now M is the midpoints and so is O, so this must be 5 across there. And also this distance here must be 4 because there's 14 and 10, so that distance must be 4. The M is the midpoint, so that's 5 and that's 5. O is the midpoint, which means this distance is 5 because this distance is 10. And also this distance must be 7 because that's the midpoint of 14. And now I'm looking for the distance between M and O. So I'm looking for that distance there, which doesn't necessarily cut through this point here. And in fact, I could prove it doesn't. And I'll give you a second to think about how you'd prove that this doesn't go through this corner. I mean, it's not relevant to the question, but whatever. It's just because these triangles aren't similar, the 4 and the 5 and the 5 and the 7. So it can't go through there. The angles will be wrong. But in any case, to work out this distance, I can just work out this total distance there and this total distance across, which is 7 plus 5 to make 12, and 5 plus 4 to make 9. And now I can just do Pythagoras. 9 squared plus 12 squared, square root is this. I could do that, or I could just notice this is a scaled up version of the 3, 4, 5 triangle. If you times it by 3, you get to this, 9 and 12 here. So this times by 3 is just 15, and I will get the answer of 15. Question number 9, how many of these sentences are true? A prime multiplied by a prime is always prime. That's actually never true. There's a counterexample to show that it's at least not always true, but it's actually never true, of course, because primes only have 2 factors, one in themselves. They don't have more factors. If you multiply a prime by a prime, those 2 primes will be factors, so this just isn't complete rubbish. A square multiplied by a square is always square. Now you could try some things here, but this is actually always true, and I can prove it with a little bit of algebra. Let's take 2 squares, 4 and 25. Now I can write them as their actual squares, 2 squared and 5 squared. And doing a bit of reverse indice laws, xy squared is x squared y squared, which means x squared y squared is the same going backwards as xy squared. So this is the same as 2 times 5 squared, which is of course a new square number, it's 10 squared. So that's always true. An odd number multiplied by an odd is always an odd, or this is a GCSE proof. If you've done GCSE proof, then great. If you're in maybe year 10 or 11, that's an odd number, this is another odd number. If we multiply them out and then collect again, we get 2 times a number, which is even, plus 1 to make the whole thing odd, so that's true. Very similar here, take 2 even numbers, multiply them together, and it's 2 times something, which means this is also even, so 3 of them are true. And number 10, this question is incredibly confusing to me, because usually in maths challenges, you don't want to do the maths that they give you, like the actual numeracy, you just want to avoid it. But in this case, this isn't hard, just do it. Just literally get a column or a grid and multiply these 2 numbers. Now, if you're desperate to do it in an intelligent way, there is a way to do it, but I don't understand why you would. The way you would do it is you'd take the information they've given you here, and you'd say, well, 53 times 57 is 43 plus 10 times 47 plus 10. And now I can just do some expanding brackets, right? So this is the same as 43 times 47, which I know is 2021, plus 43 times 10, which I know is obviously 430, plus 10 times 47, which is 470, plus 100. And this together makes 900, because 800 plus 30 plus 70 is 900, plus 100 is 1,000, so it's just 1,000 more than this. which is 3031. Sorry, 3021. Massive apologies, that I've just misread that. That should be 3021. So the answer should be D. Apologies. But yeah, I don't understand why you would do that rather than just multiply these two things together. The answer should definitely be D. Apologies for underlining the wrong thing there. But yeah, very weird. I mean, it's kind of interesting that you could prove that this relationship always holds for any numbers. If you take two numbers, multiply them, and then take two more numbers that are 10 above in each, the number is always going to be 1,000 more than the odd one. And that's kind of interesting, but yeah. Question number 11. So a couple of ways to do this. The most obvious way is to just give it a quick sketch. We can all sketch this very quickly. Y-intercept of 3, gradient of 2, so it looks a bit like this. Reflecting the x-axis, so this point is going to go down to -3. This point is going to stay where it is because it's on the x-axis, and we'll end up with this. Now, okay, well, it's clearly not this, this, or this then, because it has a y-intercept of -3. And the gradient is clearly negative, so it's not this, it must be this. That's the only one it could be. There are other ways you could do that. If you're particularly in year 11, maybe even year 10, you might have done graph transformations. So if you have a function is 2x plus 3, how do we flip a function in the x-axis? Well, that transformation is f of x goes to minus f of x. So our function 2x plus 3 goes to minus brackets 2x plus 3. Expand out the negative and you get minus 2x minus 3, which is also this answer here. Good. Question number 12. Okay, so just decimal multipliers here. To find 50% of x, you do 0.5 of x. To find 40% of something, you do 0.4 of that. So this is just going to be 0.4 of 0.5 of x. And likewise over here, 0.3y finds 30% of y. 20% of that, you just do 0.2 times that. So that's that. Multiply these out. At this point, I've swapped to fractions because I don't really like decimals when I've not got a calculator on me, which I don't for this, obviously. That's 2/10, that's 600, cross multiply, and then cancel. There are much smarter ways of doing this than what I just did. But anyway, this cancels as 20 over 6, which cancels as 10 over 3, which means y is 10 over 3x, which is this one here. Cool. Question number 13. What's the remainder here? So this is what I was saying a couple of questions ago. You don't actually want to do this multiplication and then divide by 9 with a bus stop to check the remainder. You can do that, and it would get you the right answer as long as you didn't make a mistake. But there is actually a much better way of doing it, which is, let's just check the remainder here. Sorry, that's not actually what I'm going to do because that ends up being a bit weird. What I'm going to notice about this is there's a rule for dividing by 3 and dividing by 9, which is if the digit sum of a number is divisible by 3, so is the number. So when you add up all the digits, you get a multiple of 3. That number itself must be divisible by 3. When I add up all these digits, I get 15. So this number is definitely a multiple of 3. And actually, because these digits are the same, just the other way around, this also adds to 15, and so therefore is also a multiple of 3. So all I'm doing here is multiplying two multiples of 3 together, which is going to give me some multiple of 9. If it's a multiple of 9, of course, the remainder is 0 when dividing by 9. Cool. Question number 14. So okay, what I'm going to do here is I'm going to consider this outer ring. This is quite a hard question, I thought, but I'm going to consider this outer ring here, and then I'm going to consider this inner kind of square here. Okay. Now the outer ring is made up of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 6, I think it's 5, 10, 16 of these squares. It's made up of 16 of the squares, and 8 of them are coloured in. So half of this outer ring is coloured in. But now if I broke up this inner square into these same these same smaller squares here, I'd be able to fit another 9 of them in, right? Do we see that? Because there's 2 rows there, and then 2 across here. So if I replaced all this junk with just more of these squares on the outside, I'd end up with another 9 of them. So the outer ring takes up 16 out of 16 plus 9 of the whole total shape. So let me just explain where this comes from. The outer ring is half shaded, right? Because 8 out of the 16 are shaded in. But the outer ring accounts for 16, because there are 16 of them, out of how many of this type of square I could put in here, which is 25, because 16 fit on the outside, and I could put another 9 if I broke that down across on the inside. So on the outer ring, I've got half of them shaded, and it accounts for 16 25ths of the whole shape. And I can plus the inner square here. I can think about, well, okay, opposite logic, that accounts for 9 25ths of the shape, because it's 9 of these squares in here, essentially, is the size of it. And now how much of it is actually shaded? Well, if I instead now broke it down into these little squares, I could go across here and across here, across here and across here, and I'd have 16 of these little squares, of which all 4 are shaded here, all 4 are 8, 9, 10, 11, 12. So 12 of those 16 small squares are shaded in here. So 12/16 of 9/25 is shaded, and now we can just add these results up. So we get 16,050 plus, well, I simplified this to make it not big numbers. You get this, I doubled that to make it over 100, and then I added them together for 59 over 100, which is obviously 59%. So I thought quite a difficult question. There's probably better ways to do it than what I did, to be honest. I don't really know. I should have just looked at the mark scheme and found a better way, but anyway. Question number 15. Patrick drives from this to this at this. So this is a speed, distance, time question, obviously. His drive back is an average of 45 and takes 2 minutes less. So let's say that the time it took, the distance that he's driving is d. That means both distances were distance d because he was just going from p to q, then q to p. So the distance is d. We'll say the speed for the first bit is 40, and we'll say that it took t time, which means here it must have taken t minus 2. If t we'll say is in minutes, obviously. So the first equation we can set up is his speed was 40 equals d over t. That's the first journey. And the second journey we can say his speed was 45, and that was same distance, but in this case over d over t over 2. And this looks a lot like a simultaneous equation because there's 2 variables and 2 equations. If we just multiply across the t's in both cases, we get 2 equations that are already in terms of d, so I can just set this equal to that, and of course I know I can solve this if I expand out and then sort it out a little bit. I get t as 18. Now I panicked for a moment here because then I looked at these answers like, oh no, it doesn't go all the way to 18, what have I done? But then you read the question, it's not asking you for t, it's asking you for d. So obviously we've actually got some work to do here because I put t in minutes just to make this easy. But now I can't just say, oh, t is 18, shove that in there and times it by 40 to find d, because this is in minutes, not hours, and this is in miles per hour. So let's make this into hours. So t in hours is 18 out of 60 hours, because there are 60 minutes an hour. Simplify that, I guess, to 3/10, which is 0.3 of an hour. So I can say, okay, well, it's 0.3, let's times that by 40. Obviously 4 times 3 is 12. And so we can, and then you add a 0, but then you take it away again, so it just makes 12. And that is an answer, which is good. Question 16. Cool. So we've got a distance of 2 pi here. This is a square, which means the area of this, well, I think first actually what I said was that means that the radius of these semicircles is just a single pi, which is nice. The area of this entire shape is obviously going to be this square plus these 4 semicircles. Now the area of the square is obviously 2 pi squared because it's just 2 pi times 2 pi. And the area of each semicircle is going to be a half, because it's half a circle, times pi times r squared, but r itself is pi. So this is the half, because it's half a circle, pi r squared, but that is r. Now there are 4 of these circles, so the total area is 2 pi all squared for the square, plus 4 of this thing here. Now this square both things, remember, is 4 pi squared. These cancel to just make it 2, so you get 2 pi cubed. And we just need to factorize this, take out a 2 pi squared, and leave behind a 2 and a pi. And that is the same thing as this, although they've written it the underorder to me. Question number 17. Okay, so let's do some drawing then. Rectangle PQRS. Side length of PQ is 2. Side length of QR is 4. Points T and U lie such that PQT is equilateral. So I can draw it here, and then this distance is also 2, and so is this distance. And the same thing goes on over here, 2 and 2. And it's asking me for the area of QRUT, so this trapezium up here. So okay, well the first thing I can think is I can get the height of the trapezium, because that's just a half of 2, so that's just 1. And now what I really need is this length here. So how do I do that? Well, if I could just work out this length and this length, then I could take that away from the 4 that goes all the way across. So this length here, well, again, like I've said, this is 1, so there's a 1 here. And now this length is going to be the root of 2 squared minus 1 squared from Pythagoras, which is root 3. And so is this length, root 3 as well, which means this length is 4 minus 2 lots of root 3. And okay, now I can use the trapezium formula. It's the sum of the parallel sides, so this plus this, times by the distance between them, so that's 1 divided by 2. So it's going to be 4 plus this times 1 all divided by 2. Well, times by 1 doesn't do anything. This makes an 8, so it's 8 minus 2 root 3 over 2. That divides by 2, that divides by 2 to make 4 minus root 3, and we get our answer of D. Excellent. Question 18. Which of these is closest in size? Now, again, this is one of those times where I wish I checked the mark scheme, because I probably haven't done it in the way that most people would. I don't know. I actually just wrote them out as what their decimals are. So this one is 959595, this one is 050505, next one is 960, and then it goes 960 again, then 960. And at this point I can see, well, because this 6 is bigger than this 5, this is clearly closer to 1 than this is, because this 6 is bigger than this 5. So scrap that. D, let's just write out, is 040, 040, because it repeats this one first. So 040, 040, 040. And I can again see that because this has a 4 here and this has a 5, this is clearly closer to 1 than this is. So that's not it. And again, I'll write this one out, 0.955555. And again, I can see because of this 5 here, this is clearly further away from 1 than this is. So I'm down to 2. And maybe the intention that they wrote this question with was for you to maybe write them as fractions, because that's a GCSE thing that you do, or something. I didn't. All that I did was I noticed, well, this number is slightly further away than 0.0400 from 1, because it has another number here. So it's slightly further away than 400, than 4 hundredths, no, 4 thousandths, I should probably say. Whereas this number here is slightly closer, because if this was 0.960, just all zeros, then it would be 0.04 away, but it's not. It's slightly bigger than that, so it's closer to 1 than that. So I think this is actually, I can just see, is closer to 1 than this is, because this is just ever so slightly more than 0.0400 away, but this is slightly less than 0.0400 away. So I can just see that the answer is C. Question 19. Okay, so we've got these two things here. Again, thinking back, I did this in a really stupid way. But anyway, the total area is 2 lots of PQ. So I'm just saying each rectangle has area PQ, and there are 2 of them. So the total area is 2PQ minus the overlap, because the total area of the shape, if you just do the 2 rectangles added up, you count the overlap twice. So I just have to take away 1 copy of the overlap. Okay, so that's fine. Now the overlap is a quarter of the total, given what it says here, which means the total is 4 times the overlap, I guess. Which means I can just put that there, and I can say 4 lots of the overlap is 2PQ minus the overlap, add the overlap to both sides, and you get 5 lots of it is 2PQ. Which is essentially just a really complicated way of just saying what this is saying. But in any case, what I can do now is I can notice, actually, this overlap is just Q tall and Q wide, because of course distance is also Q. So the overlap is actually just Q squared. So I get 5Q squared is equal to 2PQ. Q isn't 0, because otherwise the question would mean nothing. So I can cancel a Q from here. And now, just be careful here. Just find a solution. The most obvious solution is Q is 2, P is 5, because then you get 5 times 2 equals 2 times 5. And so the ratio is from Q to P, 2 to the 5. They've asked P to Q, so that's going to be 5 to 2. Yeah, cool. Question number 20. 2 straight lines have those 2 equations, and they meet at the point 3, 1. Now, this is a question that is tempting to do too much work for. It's because you have an intersection point, it's tempting to like set these equal to each other or whatever. You don't need to do any of that. All you need to think is, if you have 2 lines, obviously I don't know what these lines look like because I haven't found what P and Q are yet. But if they meet at the point 3, 1, regardless of the whole intersectionness of it, all that really means is that both lines go through the point 3, 1. So for both of these 2 lines, when x is 3, y is definitely 1. And that's all I need to take from this. So I'm just going to put in x is 3 and y is 1 into both of these equations, and I get this. And now this is just, I mean, I just immediately have simultaneous equations. In fact, it's easier than that because this one doesn't even have q in it. So I can just immediately solve this for p, and then I can put p into here, and I can just immediately solve that for q, and I get my answer of q is 2. So that's kind of interesting. Okay, question 21. The diagram shows some equilateral triangles. So this is an equilateral triangle, I think, and so is this. And the overlap is this kind of hexagon shape here. The areas of the smaller triangles that are in here, which are also equilateral, are these. And now, if they're also equilateral, that means that every triangle on this picture is similar to each other because they're all equilateral. So all the triangles are similar, which means if I just call this length of the smallest triangle x, now this slightly bigger triangle has an area that's 9 times bigger. But if you've done scale factors across area to length, you know that that doesn't mean that the side length is 9 times bigger. That means the side length is 3 times bigger. Because if the scale factor is 3 from x to 3x, that means the area scale factor is 3 squared, so 9. So you get from 1 to 9. And exactly the same thing for this one. The area has gone up by a factor of 16, which is 4 squared. So the length scale factor is 4. So that becomes 4x, which of course means that the side of the big equilateral triangle is x plus 3x plus 4x, which is 8x. And so to get from the smallest triangle to the biggest, that's a scale factor 8, which means the area scale factor is 64, 8 squared for 64. So I know that the area of the entire equilateral triangle is 64, so I can just do, to find the hexagon, 64 minus 1 minus 9 minus 16, and I'll get my answer of 38. So, good. Question number 22. Lovely question because algebra is very good. I'm going to make this x over x, this x plus 1 over x plus 1, and this x minus 1 over x minus 1, because of course all of those things are just 1, because it's something divided by itself. And now I can add the fractions together. So this becomes x plus 1 over x, this becomes x minus 1 over x plus 1, because you get a minus 2 there, and this becomes x plus 1 over x minus 1. Of course the denominators stay the same when you're adding or subtracting fractions. And this is great because without multiplying these out, which you definitely don't want to do, you just notice that this cancels with that, and this cancels with that, and you're just left with x plus 1 over x, which is this answer here. Excellent. Question 23. Okay, so quite a difficult one conceptually, I think, this question. The first thing to think is this semicircle has diameter PR, so clearly this length is going to be quite helpful. Now this itself is also a semicircle, which means this length is also 2, which means this length PR I can find out by doing 2 squared plus 2 squared square rooted, which is 2 root 2. Which means the radius, and of course when you're thinking about areas of circles and stuff, it's always the radius that matters. The radius is half of that, which is just root 2. So the radius of this semicircle is root 2. Now how do I go about finding the area of this? Well, what I could do is find the area of this whole semicircle. Then I need to find some way of taking away this segment here. But I can't really do that, so what I'll do instead is I'll take away the entire quarter circle here. I'll take away that whole thing, and then I can add in again this triangle. So follow that again. I'm going to do the entire area of this semicircle. I'm going to take away the quarter circle, which gets rid of this, but also gets rid of this area, which I never had in the first place and need to put back in. So I'll put it back in. I'll add in this triangle. So okay, that's my plan. So I'm going to work out the area of the semicircles. That's a half pi r squared, a half pi times this squared. I'm going to take away this entire quarter circle, which has radius 2, but I only need a quarter of it, so I'm going to take away a quarter of pi times 2 squared, and then I'm going to add in this triangle, which is a half times 2 times 2. And I'll sort this all out. So this makes 2, which cancels with this half, so that's just going to be pi. This makes a 4, which cancels with the quarter, so it's going to be pi minus pi, and this half cancels with the 2, so this just makes 2, so it's going to be pi minus pi plus 2, which is of course just 2. And that's going to give me the answer. Good, almost there. Question number 24. Stand right on the whiteboard the numbers 1 to 6. Okay, so there they are. Then P additional 5s and Q additional 7s. Okay, so I've got P lots of 5 here and Q lots of 7 here. The mean of all the numbers is then 5.3. Okay, so the mean is the sum of all of the numbers divided by the number of numbers. So how many numbers do I have here, and what's the sum? Well, I have 1, 2, 3, 4, 5, 6 numbers here. Then I have another P and another Q. So the number of numbers is 6, just to represent the first 6 numbers here, plus P plus Q. That's the total number of numbers. Now what about the sum? Well, the sum of the numbers is 1 plus 2 plus 3 plus 4 plus 5 plus 6, plus P lots of 5, which is of course just 5P, plus Q lots of 7, which is 7Q. So the sum of the numbers is that. Now the mean, as I've said, is the total divided by the number of numbers. So the mean, which I know is 5.3, is this. I can write 5.3 maybe as 53 over 10. And now I can do some cross multiplying and do some algebra and hope something happens here. So I'll cross multiply, which gives me this junk. I'll rearrange to put Q on one side and P on the other. And now I look at this and I think, okay, well, I've got two unknowns here and only one equation, so this doesn't seem very helpful. Except, remember, you know that P and Q are integers. Because she's written an integer number of 5s, you can't write 5.55s down, right? So P and Q are whole numbers. So what I did here was I thought, well, okay, this is 17 times something, which means this side has also got to be something in the 17 times table when it's all together. So let's just write out the 17 times table. And I think, okay, well, 102 is that, so P is not negative, right? So we can't get to 102. Can we get to 119? Well, to get this to be 119, I would need this to be 11, and 3 times something isn't 11, at least if it's an integer. So I can't do this. What about this? Well, then I'd have to add in another 28 to get from 108 to 136. Can that be 28? Well, no. 3 times 9 is 27, so close, but no cigar. So, okay, can this side be 53? And for this to be 153, I would need this to be 45, which I can do. I can make P 15. So I can make P 15, and now if P is 15, this whole thing is 145, which is 17 times 1, 2, 3, 4, 5, 6, 7, 8, 9. So Q is 9. And that's the smallest possible value. It's smallest, of course, because there are bigger multiples of 17 I can make this, and then I can make Q bigger as well, but that's the smallest one I can get. So Q is 20, is 9. Really well done if you got that. I thought that was a tough question. Question 25, another speed, distance, time question here, which I've probably done in a stupid way. Tom has speeds for walking, running. Let's call his running speed R and his walking speed W. And now, if you're on an escalator that's moving, your speed is going to be, and you're moving as well, your total speed is just going to be the speed that you are moving at plus the speed that the escalator goes. So if we call the escalator speed E, and you're walking down this escalator, your speed will be W plus E, if we call walking speed W. You just add the speeds together. So this is going to be my plan. Tom can run down it in 15 seconds. Now let's call the distance that you go on this escalator D again. And that means that his R, speed when running, plus the speed of the elevator is his total speed. That equals D over 15. Okay, and now I'm going to set that up again for his walking. So walking plus E, because the escalator is going this time. So W plus E is that same distance, but this time over 30 because it took 30 seconds. One day the escalator is broken, and it took Tom 20 seconds to run it down it. So now his speed is just R, still the same distance he's traveling, and it took 20 seconds. And now somehow I've got to sort out all of this to work out how long it would take to walk down the broken escalator. So I need T when he's just walking. Okay, so how do I do this? Well, this just took a lot of sort of playing around with some algebra on my part. So what I did first was I said, well, R is D over 20. So let's put that into here, because that can give me an expression for E in terms of D. Because I can move the D over 20 over, I can add those fractions together, and I'll get E is D over 60. Now, what this means is, essentially, if you were standing still on an escalator, you weren't moving, your speed was 0, it would take you 60 seconds to get along the escalator to the other end. But more importantly, what this means is I can put this expression for E into here, and then I can work out what happens if you're just doing W, which is, of course, is what I want. On a broken escalator, how long does it take? So let's do D minus 60 on both sides, and then again, you can do proper fractions here, or you can just skip to the ends like I did. And now I can see, okay, if you're just walking, the escalator speed being 0 because it's broken, if you're just walking, it takes 60 seconds. The time is 60 seconds to get through the same distance. So it's 60 seconds to do it just walking. And that'll be our answer. Really well done if you stuck through that, and good job for preparing yourself for Intermediate Math Challenge by watching videos like this.